are you ready for some more wonderful times in physics? Because I am. Here's some energy review problems to kickstart your energy learning. If you know me, it's no secret that I am a huge fan of Lord. Okay, this is where I really started to kind of make some of the problems kind of silly. Okay, Lord decides to literally drop her fourth album. Hopefully soon. The album is dropped from a height h above the floor. The album slides, so we're approximating the album as being like a block, okay? The album glides down a smooth, frictionless track until it reaches the floor at point A, where the track curves and projects the album at initial angle theta to the horizontal. And we're going to write some expressions here. Okay, so the velocity of the album when it reaches the ground, that is a simple energy conservation problem. Okay, at the top here we have mg capital H because we have gravitational potential, right? We initially have it at rest, and then when it hits the bottom, all of it's been turned into kinetic. 1/2 m. I'm gonna call this VA because it's at the velocity at point A. Okay, so all I gotta do, right, is take mgh and set it equal to 1/2 mv sub a squared. Oh, sorry, that should be squared right there. That's my bad, okay? Okay, and what you should notice is that the mass doesn't even matter in the grand scheme of things. Okay, mass doesn't matter because it's in both terms. So we get g capital H equals 1/2 v sub a squared. And to get the rest of this going, right, you multiply the 2 on both sides to get 2gh equals v sub a squared, and then you can square root to get v sub a equals root 2gh. Okay, all right, so there's your velocity at point A. Okay, that's how fast it's going when it hits the ground. Okay, okay. All right, at point B, the velocity of the album when it reaches point B, the highest point in the projectile trajectory. Now, you actually don't really need to do any math for this. Maybe a little bit, okay? But it's important to note, right? Do you see that this is basically, right? This is basically right here, kind of like basically the same as launching off of a cannon, right? When the album launches, it's going to have some initial speed here, okay, going off the cliff, okay? And what we should know, okay, is that at B, okay, right, we have some initial velocity that we're being projected with. It's being projected with a velocity VA right here. And that velocity has components, it has a horizontal and a vertical component. Well, at point B, there is no vertical component. It's all horizontal. Now, we can't just say that the horizontal component is equal to VA because it's not true. It should be the same as the horizontal component as it is when it launches, though. Okay? So therefore, at point B, all velocity, okay, is horizontal, okay, and same as when it launched. Okay, so v sub b should really be equal to v sub a times the cosine of theta, okay, because that would be the horizontal component of when it launched. Then I can just take what I got earlier for v sub a and plug it into here, and you get v sub b equals root 2gh cosine theta. And that's an expression for b right there. Oh, I cut off the theta when I boxed my equation, okay? But the theta is still part of it, okay? And you should notice, right, that the root only goes this far. It only goes out to the h, okay? We're not taking the whole thing. Okay, to figure out the maximum height h that the album reaches while it's a projectile, I'm going to use conservation of energy, and you can actually use conservation of energy from the very beginning to here, right? The types of energy that are present, right? Well, we have mg capital H up here. Here, it's going to have mg lowercase h plus 1/2 mv sub b squared, okay? Okay, so when you do that, you can just set them equal to each other. mg capital H equals mg lowercase h plus 1/2 mv sub b squared. And you're like, okay, wait, Mr. Mitchell, you made the m really big here, but guess what? It doesn't matter because you can actually cancel out your m's. Boom, boom, boom. Okay, it's like what happens if you don't subscribe to my channel, right? You're canceling out the M in your life, and I'm the M in your life because my name's Mitchell. Okay, okay. So you end up getting this expression right here, which is just G capital H equals G lowercase h plus 1/2 V sub B squared. Okay, I want to get the little h. Okay, so all I got to do is get that by itself. Okay. And I'm actually contemplating, would it be easier to, well, I'm gonna move around first and then substitute the V sub B back in. So I'm gonna move this to the other side as GH minus 1/2 V sub B squared equals G sub H, and then I can then move that to the other side here. Oh, did I get the snap? Did I get him? Dang it, I didn't. Okay. Um, you divide G on both sides, okay, and you would get, lowercase h would be equal to G capital H minus 1/2 V sub B squared all over G. Now, you'll actually be able to cancel some stuff out here in just a second, because when I expand V sub B to include this will become H equals G times capital H minus 1/2. Okay, now I got to square this. So this is going to end up being 2GH, which is all now out of that radical. Okay, it's now all out of the radical, times cosine squared of theta. Okay, and then I divide the whole thing by G. And you should notice that this becomes a lot easier because you can actually factor out your G's, right? You can cancel out your G's, okay? And you should be left with H minus 1/2, 1/2, oh, the 1/2 and the 2, by the way, those can also cancel out. So you're left with H minus H cosine theta, or H cosine squared theta, okay? So you should get H equals, and I'm actually going to factor that out here, H, parentheses, 1 minus cosine squared theta. Okay? So that's how you'd get that. That's a long process just to get right to this point. Okay? Okay. All right. So that's how you can do that one. Okay, let's look at this problem on the incline. So there's actually a homework problem very similar to it, and this one is kind of tricky for one big reason, okay? You know that at the top, right, so this is a block of mass m, 5 kilograms, set on inclined plane of theta equals 37 degrees. Block has coefficient of kinetic friction of mu equals 0.25 on this incline. The block slides down the incline distance d equals 10 meters before striking a spring of spring constant K equals 120 newtons per meter. After striking the spring, the block travels an additional distance x before coming to instantaneously to rest. Determine the distance x that the block compresses the spring before coming to rest. Okay. So what it's asking us, right, is that it's really asking us for x here, because what's happening is the block's going to go and it's going to hit the spring, and the spring is going to and then we were trying to find how far is it stretched at that moment, because immediately after that moment the spring will push back and push the block back up the ramp, okay? Or we can assume that, right? Now, it's important to note that one of the things that's most challenging about this problem is that at the beginning, okay, is that initially you have gravitational potential energy, mg delta y, okay, mgy, and then at the end you should have it all turned into spring potential, but there's also some dissipated, okay, because there's kinetic friction. So you should have, right down here is going to end up being spring potential 1/2 kx squared plus force of friction times d. Okay. Okay. And that's what you got to do. Okay. And here's the thing now. This is the part that's most challenging, right? I'm going to set these equal to each other. mgy equals 1/2 kx squared plus the force of friction times d. Okay. Now, here's the thing. I actually do have to make some substitutions here to put it in more in terms of the problem more. Okay. Um, mg. So what's y here? right? The distance y, we're going to consider the lowest point the block goes to be 0 level, okay? So really, it's really what we're trying to do is we're trying to get here, okay? Oh, wait, can I do that? Okay. We're really just trying to get there, okay? And then, okay? Okay. So really, right, do you notice that I was able to make a right triangle here? Okay. And I can actually figure out the distance here because this is going to be y equals, I'm going to call this part right here, okay? I'm going to call this capital D, which is going to be D plus X. Okay, so that whole length right here, I'm just going to call this capital D. Well, this is capital D, and then my angle is right here, theta. This is D sine theta, okay? And really, that's the same thing as saying, d plus x sine theta. Okay? I'm writing really small here. I'm going to have to leave myself a lot of room because this problem is kind of lengthy. Okay? Okay. And when you have all of this set up now, okay, wait, I got my y, okay, x, d right here. I'm going to call this, by the way, this is going to be capital D, right? F friction times capital D because it's the whole distance. So when I make my substitutions, I'm doing mg d plus x sine theta, okay? Let's see, where is it? Mg d plus x sine theta, d plus x sine theta equals 1/2 kx squared plus the force of friction times d plus x. Okay, because that's the whole distance that it travels. Okay. Okay. All right, so now I can make some substitutions in here. I think I've got everything in a pretty solid point here. Okay, which by the way, I want to make, or I want to do a little aside here and tell you that force of friction, right? Well, that's normally mu normal force. Okay, and in this case, right, the normal force is not just going to be mg; it's actually going to be a component of the gravitational force. Okay, so it should be mu times mg cosine theta. Okay, that's how you get that. So when I make all my substitutions in there, this is going to be a really, really long equation. Okay, it's going to be something that's really, really confusing here. Okay, I should get mg d plus x. Okay, so mg, the mass is 5, g is 10 for simplicity. D is 10, but I don't know what x is. Okay, sine theta, am I given the angle 37 degrees? Sine theta, by the way, okay, that's about 3/5. Okay, set it equal to 1/2. The spring constant is 120. We don't know how far it's compressed. The force of friction is going to be, actually should solve this out to the side. The mu is going to be 0.25. The mass is given to us as 5. G is 10. Cosine theta. Cosine theta is 37, which is approximately 4/5. That's from the Physics C formula sheet. And then that should actually give us, let's see, I don't have my calculator with me. This is about 50. 50 divided by 5 is 10 times 4 is 40, and 1/4 of that is 10. Okay? So I should get 10 for the friction force. Okay? 10 times d plus x, d lowercase d is 10. Okay, and then we don't know what x is. Okay? And you're going to have to see that I'm going to have to make a lot of simplifications here. 5 times 10 is 50. That's 10, 30. Okay, that becomes 30. So this becomes 30 times 10 plus x. On the left-hand side, this is 1/2 of 120 is going to be 60x squared plus, and this will become 100 plus 10x. Okay? And then this left-hand side is going to be, okay, 30 times 10 is 300 plus 30x equals 60x squared plus 100 plus 10x. Now, what you should notice is that this is going to ultimately give us a quadratic equation, which we then have to use the quadratic formula to solve. So what I'm going to do, right, is I'm going to subtract the whole left-hand side from the right side, okay? And you should end up getting, when you rearrange all your values and all that fun stuff, you should end up getting 60x squared minus 20x, okay, minus 200. Okay, and I'm rearranging some of the terms here because so we don't have any leading negatives, but also I like to put them in terms of like x squared, x, and then I guess like x to the 0th, right? Okay. And then you can actually simplify this further. This becomes 0 equals, and the way I simplified it was by 20. Okay, so I got 20 out here, and this ends up being 3x squared minus x minus 10. And I don't think there's a way to do this like super cleanly because you can't really figure out what adds to get this and multiplies to get that. So I would use the quadratic formula here to get x equals 1 plus or minus the root 1 squared plus 4 times a, which is 3, times c, which is 10. That gives me 120. Okay. And then when you divide the whole thing by 6, okay, because that's 2 times a, which is 6, okay, and that gives me x would have to be equal to 1 plus or minus 11 over 6, which means that you would have to do 2 meters, okay, if you take the acceptable result. Okay, let's see. 1 plus 11 is let's see, 1 plus 11 is going to be 12 over 6 is 2. 1 minus 11 would be negative 10 over 6. And that just wouldn't make any sense because it's negative. Okay, so it would have to be the positive result there. And that's the only way that that would make sense. Okay. And the next example is a bungee jump example. So for Barbie bungee jump, which is the performance task that we do in Physics C, this is pretty helpful to know. Okay. So first off, this is an Impractical Jokers example. It's Impractical Jokers example with Murr. If you know who Murr is, he's the bald guy. Okay. He's forced to bungee jump off a bridge. Murr has a mass of 100 kilograms. His cord has unstretched length of 20 meters and spring constant of 20 newtons per meter. Turn me to the following, assuming that Murr does not strike the ground. Okay, hopefully he doesn't strike the ground because that would be really bad. Okay. Determine Murr's speed when the cord just begins to stretch. So notice that the cord has an unstretched length of 20 meters, which means that he can fall for 20 meters, okay, before the cord actually starts to stretch and pull him back up. Okay, so over the course of the fall, we can see that GPE, or gravitational potential energy, is turning into kinetic energy over the 20-meter fall. Okay. So if we do mg delta y, okay, set equal to 1/2 mv squared, okay, I need to get v by itself, right? Because that's what I'm trying to figure out. So I'm going to multiply by 2 to get 2mg delta y equals mv squared divided by m. Okay, I get v squared equals and if you actually, I don't even need to show you this step, right? Because it just ends up being that the m's cancel out. Okay, I'm losing my mind. I'm crashing out. That's what the c stands for. And you get 2g delta y, and then you just square root both sides. So I would get v is equal to root, and I'm just going to plug in my numbers here, 2 times 10 times the 20. Okay. Can I do this in my head? Let's see, 20 times 10 is 200, times 2 is 400, and you can actually take the square root of 400, okay, and it ends up being a nice number. It should be 20 meters per second. So he should be going 20 meters per second after 20 meters of falling right before the cord starts to stretch, okay? How about when his speed is maximized, okay? If his speed is maximized, okay, this means that acceleration is equal to 0, right? If it's maximized, he's not accelerating anymore, okay? He also shouldn't be decelerating at this moment either. So this means that acceleration is equal to 0, which means that the net force should also be equal to 0, okay? So if that's the case, when his speed is maximized, that means that the spring force from the cord, the elastic force from the cord, should cancel out his mg. So therefore, I can just say kx needs to be equal to mg. Okay? Well, k is 20. We're given that in the problem. X we don't know. Okay? And that's actually what we're solving for. M is 100. G is 10. Okay, 20x equals 1,000. Okay, that's easy, right? You're thinking this is kindergarten math, right? X should be equal to about 50, okay, meters. Okay. Okay. Now, not out of the woods yet. Okay. Um, Not out of the woods yet here though. Okay. Because this is not how far he's fallen. This is how far cord is stretched. Okay? So add the unstretched length, okay, to get distance below bridge. Okay? So what I'm going to do, right, here's x. So really the total distance, okay, total distance is equal to x plus delta y, okay, and that's going to give me 70 meters, okay, because the cord doesn't stretch until you hit that 20-meter mark, okay, and then after that it begins to stretch. So this is saying the sum of the stretch of the cord plus that unstretched length is actually how far he is below it. Maximum speed, well, we can figure out where he is when his speed is maximized 70 meters, and I'm just going to do conservation of energy again, okay? I love conservation of energy. I use it so often, okay? Because gravitational potential energy is going to turn into not just kinetic energy this time, but also spring potential energy, okay? So when I set this up, I'm going to do mg delta y equals kinetic energy, which would be 1 half m v squared, okay, plus 1 half kx squared. And I've already got pretty much all the values here except for v squared. Okay, v squared is the only thing I don't know yet. So I'm going to plug everything in. The mass is 100, okay, times g is 10. Delta y is the distance below the bridge. That's going to be 70. Okay, I'm going to use 70 for that one. And then 1 half of m. Okay, well, his mass is 100, so the half of m should be 50. V squared plus 1 half times k. Okay, that's 1 half of the spring constant, which is 20. So that's going to be 10. And then the stretch of the spring or of the cord is going to be 50. So 50 squared, okay? And this is going to give you some really big whopping numbers, okay? That's going to give you 100 times 10 times 70. That's going to give you 70,000, okay? Set that equal to 50 v squared, okay? Plus, and then you do 10 times 50 squared. That's going to give you about 25,000, okay? All you got to do now is just solve. So if you subtract the 25,000 from there, you should get 45,000 equals 50 v squared. Divide the 50, okay, and you get 900. And then you should see that v would have to be equal to 30 meters per second. So you're like, wow, we're using really big numbers. Is Mur like okay? Yeah, he's fine. He's actually going a pretty decent speed at the end of that. How far does he go when he comes to rest? That's a good question. So this is talking about when he comes to rest. I should probably say this is momentarily. So if you've ever been bungee jumping, what you know happens is that you jump down and the cord stretches and it slows you down at the bottom of your fall until you hit, the bottom of like the maximum stretch of the cord or whatever, and then you're momentarily at rest and then it flings you back up. That's how bungee cords work if you've ever been bungee jumping, or even if you've ever done something like the Barbie bungee jump where you've got like a stretchy cord or something, or even if you put like a mass on a rubber band, right? And then you let it go, it'll go down and then it'll reach a minimum height where or a minimum depth where it'll come momentarily to rest, and then it'll go back up and oscillate. Okay, and that kind of gives some spoilers to the next part. Here we're talking about gravitational potential energy turning into spring, because at the bottom of the motion you're not moving, so all of it has to become spring potential energy. Okay, mg delta y equals 1 half kx squared. Now you're like, this isn't that bad, right? It's not that bad, okay? It's not really that bad, okay? sort of. Okay. Now, it's important to note, right, that delta y, again, should be the stretch of the cord. So we don't know how far down he is when he comes to rest. What we do know, okay, is that, and I'm going to make myself a little like box here so that you know that this isn't connected, okay? What we do know is that delta y is equal to x plus the unstretched length, which is the 20 meters, okay? X is the spring stretch right here, okay? So if I replace this right here for delta y, I would get mg x plus 20 equals 1 half kx squared. And now you might be able to see where things get complicated, okay? Where things get a little bit weird. If I distribute, okay, I should get mgx plus 20 mg equals 1 half kx squared, okay? And then I'm going to plug everything in. The mass of myrrh is 100, okay? G is 10. X we don't know, so I'm going to leave that there. 20, the mass of myrrh is again 100, G is 10, and I set that equal to 1 half. Spring constant, what was it, 120? I keep forgetting. It should be, oh no, it's 20, right? It's 20, right? I can't see it because I've got my document camera over it. It's 20, right? Okay. 20x squared. Okay. Now, you should notice a couple of things, right? This is going to simplify to 10, and then you get a couple of other things here. So this should be 1,000 x plus the 20 times 100 times 10 is going to give me 20,000. Okay, and so that equal to, that's going to be 10x squared. Now this part is where hopefully you recognize that things are going to get really tough here, because if you subtract this side, you'd end up getting 0 equals 10x squared minus 1000x minus, that's 100, 1000x minus 20,000x, or sorry, no x, sorry, it's just 20,000, okay? And now this is where things get weird, because now you actually have to use the quadratic formula. And I'm going to skip that step because I trust that you know how to do it, okay? If you want to see the whole steps, you can get there, right, yourself. But the two answers that you should end up getting are x equals 117 and x equals negative 17. And you should recognize that this positive one is going to be the one that we need to stick with. Okay, because this wouldn't make any sense for us to like go back up a position. That ends up above the bridge. It just doesn't make sense, right? So this is going to mean that delta y is equal to 117 plus 20, so it ends up being 137 meters is where he goes. Okay. Explain qualitatively how his motion is over a long period of time. Again, you ever go bungee jumping, you ever drop something off with a bungee cord, you'll notice that what happens is the object goes to a minimum like depth kind of, and then springs back up, and then keeps going down, and it goes down to a new minimum depth, and then it springs back up. What's that called, right? That motion, wah, wah, wah. That's called oscillation, right? So he'll oscillate, okay, or bounce up and down, okay? Okay, and that hopefully should make sense. Now, how far below the bridge does Murph finally come to rest? It should be at the same location where forces balance. Okay, so that would be when there's a stretch of 50 meters, okay, which is 70 meters below the bridge, okay? Okay, so that's going to be kind of how you can you can solve problems like that, right? That's a bungee cord example. You'll see that in like Barbie bungee jump, all that fun stuff. Okay, that's that, right? That's the whole thing. Wow, it felt like it took forever. It probably did. Okay, all right. Live, laugh, love. Live, laugh, love. All right, bye.